What we all need to tackle are upcoming challenges on storage. This is unquestioned that the amount of data stored will still exponentially increase. About 100 times in the next 20 years, 100 times we need to save 100 times of energy, we need to be 100 times faster to store all the data, 100 times more sustainable. Otherwise, it would just consume all the energy of the planet. The problem is actually that the current storage technologies are running slow on scaling. So they reach the potential of exponential growth, which means there is a gap opening, which will lead to higher prices and the supply gap and the bottleneck. And this could probably cripple AI business models because storage was not calculated, or expensive storage wasn't calculated into the business models. So there is a new technology needed for the AI era. I say AI era, not only for AI, but everything which is connected with AI and machine learning. Storage is either expensive and high-performing, or it's not expensive and low-performing. For the coming AI applications, we need storage which is fast accessible, with a high write-read speed, and it needs to be very cost-efficient.
Isn't there one aspect of this waste, though, that a lot of the data we store is duplicated, very low quality, and we can address this storage gap two ends. One, by getting better storage, the other way, by not storing everything twice over.
Absolutely right. Yeah. Who creates the policies? I mean, there's a statistics. Every second, 50,000 images are taken with smartphones worldwide. I don't know how old it is, but the range of numbers is about accurate. 50,000 images stored in the cloud, redundant, duplicated on several places. That means it's one hard drive per second, which need to be inserted in a data center worldwide. It's 86,400 hard drives a day, which need to be also replaced. So that's electronic waste and so on. So this is only images. So we can imagine there's lots of data which needs to be stored. And the question is, do we need to store it? I don't know. It's not what we discuss here, I think. Yeah. Long-term storage, especially, when it comes to keeping photos for a lifetime, or data on archives, or science data, or business data, which need to be kept for 10 plus years. Usually it's energy consuming, it needs to replace media, it needs to migrate, it needs fixity check, data maintenance. These are the driving costs of long-term data storage. And really the question is, how could we pass on our digital heritage to coming generations? So these are some of the challenges storage needs to solve in the coming decades. The last one, as Fred already said, my background is artist with a focus on ceramic. I started in Linz Art Academy and initiated a project about 15 years ago pointing to the problem that nothing will be left from the digital age if we don't take action. The threat of a dark digital age is, I think it's about the 2000s. It was the first mentioning. 𝗬𝗀𝗃, the father of the internet, proposes this in several TED Talks and presentations. We need to do something. And with my background in ceramics, I know there's a print with ceramic colors. I misused this to print it on tiles, to store images and text on ceramic tiles. Storing this in the old salt mine in Austria called Memory of Mankind project to point to the problem, if we don't take action now, nothing will be left from our age. This is a kind of cultural, scientific project to keep a snapshot of our era. This was images and text on bathroom tiles. Still ongoing project. A couple of years later, when I started, I thought, well, image and text is not efficient enough to give an image of our time. It would be music and video and gaming, so I started to develop digital data carrier on ceramic basis. I was looking into other technologies already existing. None of them seemed to be ready for the market within the next decade, so this is the reason why I started myself. With a research program at the Technical University in Vienna, the idea with some people I met during my presentations, technicians and business developer, to try to write with a femtosecond laser on thin ceramic. Thin ceramic applied on thin glass foils. Thin glass foils, as you know from your protection foil from the smartphone, thin glass foils are massively produced for the display industry. So there is the data carrier, which we are envisioning was thin glass with a dark ceramic layer, punching holes representing zeros and ones into the dark surface, and reading with a microscope optics and the CMOS sensor to read the images we were writing. So this research program was successful, funded with over €1 million by Austrian research promotion entities. We still have our labs at the Technical University in Vienna. It's an interesting collaboration. So this was the start of Cerabyte. And now well, that was my origin, go into the details and some tech deep dives into Cerabyte. So the media itself, it's thin glass sheets with a dark ceramic layer, as I said, and punching holes into it. But not only single holes, but data matrices with a kind of laser stamp. I will explain this later on. So these are physical bits. This is ablation of the ceramic layer. The ceramic layer is very hard, and it takes quite a energy to ablate to create this hole. This hole stays there forever. It doesn't close. And where there's no hole will appear. This is important because there is no bit rot. The glass itself, it's raw material, a very simple processing actually to get the ready data carrier. It's some tens of steps compared to hard drives or SSDs, where there are probably hundreds or maybe 1,000 steps until it's the first time ready to be written with data. This is just glass in a production process for the display industry, hundreds of square kilometers per year, and the PVD coating, which is also applied for solar panels or glass for high rises and so on. So the production is actually very, very easy, and you can understand that the media itself is absolutely low priced. How does the writing work? So we take, as I said, a laser stamp. Usually optical writing was associated with writing single spots. So that's the limitation of optical writing on a rotating disk. You can't speed it up, otherwise it just breaks apart, and you always write single bits. What we do here, we use a digital mirror device, which has been developed for the semiconductor industry about 15 years ago for maskless lithography. Today, this device is built in every projector, like here, in every head-up display, in matrix headlights of cars. So this is a comparably cheap component. What it does, it projects the laser beam onto the digital mirror device, and the digital mirror device projects the images of data matrices. And this goes through a microscope optics and gets miniaturized onto the surface of the data carrier. And when light was reflected from the mirror, there is enough energy to create holes. So there's a little animation. Hope this works with video. Oh yeah, okay. There should be music, but if there is no music, I don't mind. So a laser spot is projected on the digital mirror device. These are 2 million tiny mirrors, each of them separately switchable with kilohertz. And then images of the data matrices are projected and run through a microscope optic.
How do you verify the writing? I mean, I assume there must be some known possibility of one of those mirrors malfunctioning or something.
Oh yeah, sure. Yeah.
So
there's
how do you verify
error correction. We'll come to this. Okay. Yeah. So this is basically how it works, the writing. Here we go. On the bit level, of course, data matrices, error correction, erasure coding, and what is very important when we're talking about a long-term storage, we're talking about an open codec. So to give everything an IT expert in the future needs to create independently his or her own reading device to get access to the data and information. So this is done hopefully ending in an ISO standard, not only for Cerabyte, but for every long-term media. Together, I mentioned 𝗬𝗀𝗏 already. He did work on this called 𝗬𝗀𝗿𝗏𝗰 about 10 years ago. It's the head of, or former president of the 𝗖𝗀𝗿𝗆𝗍, 𝗂𝗃𝗏𝗆. It's the Digital Preservation Coalition. So there are a couple of entities working together on this open codec. Just want to mention it because this question comes immediately when we're talking about long-term storage. So how is it read? We read through the same microscope optics with a high-speed camera with a CMOS sensor. Actually, this is done with a smartphone QR code reader. So it takes an image, a capture of the image, reconstructing the code, and then with the same algorithms, decoding the data. I have a sample here. There's a microscope, there's a data carrier. We're writing here with QR codes, which is not the final matrix we are writing with, but here you can take your own smartphone QR code reader and decode what is written on the data carrier. This should somehow demonstrate, as long as the algorithm is known, data is readable. So how are they stored? These sheets, now we have 100 micron thick glass foils, like bendable glass. So it's similar to the glass you know from the foldable phones. So that's also glass. As long as the rim is sealed, you can almost fold it all together. 180 of these foils or sheets are stacked in cartridges with the form factor of LTO tape, which means we can leverage the library automation of tape. And customers can easily switch from tape to Cerabyte using the same automation facilities and library automation. We have random access, so we just open the cartridge and separate the stack where we want to read. So we don't have to wind 1 kilometer of tape, so the access is quite fast. And
you have to go through every layer then. So
no, we can separate it.
Yeah, okay, that I understand. But so, say you want the 100th piece of it, you have to get it out, read it, and then put it back in.
Right. Yeah.
So, are you already working on what they do with hard drives as well? So something multi-layer instead. It's kind of multi-layer, but now you have to get everything out.
Yes.
Already working.
It's a very important decision to have it only in one surface on the layer, because when you take a snapshot or a capture of a photo, the signal-to-noise ratio is excellent. If you have to go into several layers where you read through layers you don't want to read, the signal-to-noise ratio becomes quite weird, and you need a lot of, well, algorithm or different angles or many captures to reconstruct the actual code. That's true. That's on the cost of volumetric density, but reading speed is crucial. This is what we learned with talks with the hyperscalers. Volumetric density is not the big issue. Reading speed and performance is.
Yeah, I've got some questions. First, for the writing, it's just by a kind of batch that you that you send the writings, or you can do it continuously.
Right.
Second, do you rewrite as an object store new things when the data is changed?
Yeah, it's by default a write once media. Write once, read forever, as we say, 𝗲𝗏. Immutable, and that's not the bug, it's a feature. Usually data is stored, which is kept, let's say, for 1 year on hard drives, will not be changed in the future. And if you just store a new file and have the old one as a track record.
Yeah, but I will take, for example, a sales. I say, today I have sales, I don't know, 20 objects. Tomorrow I have sold 5 more. In my dashboard I need to have 25. And that somewhere the data must change.
Okay, so Cerabyte is actually...
My question is, do you rewrite something on the glass?
Yeah.
Or do you change the data which was already on the glass?
Yeah. Okay. To be more clear, Cerabyte is not a medium where you have data on a daily basis or within... Yeah. It's an archival medium. So, as I said, usually the data stored on Cerabyte is not going to change in the future. And even if you can write additional files and have the track record, when you want to delete it, that's here, you just crush it and recycle it. It's 100% recyclable, just glass. The thin ceramic coating is only 50 nanometers compared to 100 micrometers of glass, so it doesn't matter at all.
So how big is an LTO disk at the moment?
The LTO cartridge.
Not the size, but how much data can...
We have 180 sheets in it, and with the data density today, where we're starting, is 1 terabyte per cartridge. So that doesn't sound very much, but it's a beginning. So it's a question of scaling how small can we write and how thin can we have the data carriers. And there's also some potential in the way of coding also to increase data.
Do you see possible evolution with the DLP system because they can be much more dense in the future?
Yes, I will come to this, yeah.
So, can you tell us read performance comparison with maybe LTO? Yeah,
so what we're doing right now is megabytes, because we just use this as GPU for our testing, because we need to test how much error correction we actually need to create our data matrix. Next step would be FPGA, and then, of course, ASICs. And that would lead to writing and reading speeds of gigabytes per second. Yeah? You imagine it's the 2 million bits per second with the digital mirror device, and 5,000 times per second to reach writing speeds that are necessary in the future. But there's more to come about future roadmap.
About the legal aspects of this, do the courts recognize this as authoritative records to be kept forever?
You mean about the files, the legal ownership?
It seems to me that if you're going to store stuff forever, then there will be a legal requirement.
Well, that's the customer's issue. It's not our issue.
Oh, well, okay, but
we don't do it as a service, so we.
Okay.
Yeah.
But it's
that's actually a good one, because with GDPR, something needs to be done. How would that work? So you say, yeah, that's for the customer, but they need an option.
Oh, well, they can just withdraw the data carrier and destroy it. Or if it's just a section.
So you will give them the option to get the cartridge, the slate that they need to get, and get it out, and that's...
That's one way. Of course, the other is to...
just mask when you when you restore the data is all backup product. All backup product that does not.
It has to be because it's write one, so it has to physically go out.
Yeah, so there's several options.
But then you can argue that it's the customer's responsibility to what they're storing. So if it is GDPR data, then maybe they should think about whether this data sets need to be included.
Yeah, you can also delete the index, of course.
Or they need to anonymize it before they store it.
Yeah, that's
research data.
So this is a summary of the properties. So we tested to almost 0 Kelvin and heated up to 500 degrees centigrade, and it's water and corrosion resistant, EMP proof, salt water. At the last OCP in Dublin, we had in the Innovation Village, we had a water kettle, a glass water kettle, and kept it at 90 degrees, not between 90 and 100 degrees, for 2 days. Our data carrier in the boiling water. Salt water, saturated salt.
Two questions. First, what are you selling us? Are you selling us something physical or something virtual in the cloud?
That's a physical, technical solution. This was the salt water thing in the water kettle. 2 days, after 2 days, the water turned brown because the kettle already corroded, but the data was still readable on our Cerabyte medium. It doesn't require energy. It's, as I said, immutable. You don't need data migration, replacement of media. It's, as I said at the beginning, there is no bit rot. There is no decay of data. Unlike on SSD or hard drive, just data disappears over time. It's deletable and recyclable, and it doesn't require any valuable materials or raw earth. That's supposed to be a very short video about the media stress test we did on a different occasion, putting into glass, into a glass kettle. That's what the same glass kettle, but this is just normal water. We did this at the 𝗬𝗃𝗃, I think in Belgium last year, a live presentation to boil it in water, and then put it in a pizza oven together with the pizza. And we had to scale down the temperature from 500 degrees to 250 degrees for the pizza, because the pizza can't stand 500 degrees. And afterwards, we put the data carrier under the microscope and projected it to the screen, and the audience with their smartphone could still read the data. So that was a very funny presentation and gave us a lot of credit, so in the aftermath.
If somebody puts one of the bunker-buster bombs down next to you, you have bad vibration.
Yeah, right.
Imagine the vibration effect.
Yeah, so this is about also, we are testing about earthquakes and so, yeah. Yeah. I don't have any numbers for this, yeah.
So different question. How do you differentiate from DNA?
I will come to this later.
Okay.
So, from the perspective of where is Cerabyte located in the storage stack, when it's taken from the access time, we are in the range of seconds, and the price is projected to be about $1 per terabyte in the 2030s. I can share the presentation afterwards if you like. Yeah. Okay. Yeah. So there are several impacts. Obviously, CO2 savings, because if you don't need to replace, you save a lot of resources, energy, and CO2 carbon emission. A societal impact. Today, everyone can store his memories for a lifetime in the form of photos or videos in our externalized long-time memory, the smartphone.
It has social problems too. There are some things you want to forget.
Right. You can still delete it from your smartphone, and I think hyperscalers will find ways to delete it also here. But also about passing on the digital heritage. This was my original aspect was on why we should do something permanent. But it's also unlocking new potentials. If you have a storage possibility where you can access data, huge amount of data, very quickly warming it up and process it for, let's say, machine learning or AI applications, then you can monetize the data you store, usually on code where you don't have any access anymore. Aspect of data security, immutable, as I mentioned already, there's big interest from military side. And now coming to the roadmap. So we built a prototype end of 2023, only made of commercial off-the-shelf parts. So to very quickly assemble something which has a footprint of data center rack with the library automation for LTO cartridges to demonstrate quickly to write, store, retrieve, and read data on this material. As I said, it was just commercial off-the-shelf parts that don't really fit together. What we did since then is improving the single components, getting the data structure down, being more precise, getting our own code to be more efficient than QR code.
But going back to the problem of accessing this in 500 years' time, the closer you get to commercial off-the-shelf parts, and the more robust it is compared to those
That's true, yeah.
stuff,
Yeah.
better.
This is why we use QR codes, because that's a standard everyone is using, and it's probably around still a long time. Yeah. And expecting to deliver 2027 the first commercial systems, and the TCO model, well, compared to hard drive and tape, because we are leveraging existing technologies. As I said, the glass is from the display industry. The PVD coating is done in huge amounts. The DMD is produced for projectors. The smartphones industry drove the CMOS sensors to incredible miniaturization. And the tape library, we use a German company, BDT, but also talking with Spectra. So this is why we need to develop or invent the wheel newly. So we're taking what is existing and putting it together. And this is a long-term roadmap. So at the moment we are here. We are starting with UV light to get the structure size down. And we already tried with focused ion beam to write the smallest QR codes ever written with 50 nanometers. That's approximately here. That's what we are testing with ion beam matrices. This is used for the semiconductor industry today. And as I said, we are using the DMD, which was developed 15 years ago for the maskless lithography. What we are testing right now is already what is used for semiconductor industry. It would be way too expensive to use it for storage, but when these machines are amortized, we can easily adapt it for storage. That will lead to the data densities that will be required in 10, 15 years from now. We already made structures of 2 nanometer size with single helium beams, so on our material, just to demonstrate it's possible, and to demonstrate this roadmap is plausible. And this is why big companies are investing in Cerabyte. As you probably might have read, it's Pure Storage and Western Digital invested in Cerabyte, and there is also others which has not been disclosed so far. One of the big hyperscalers, because they see the problem coming.
See, one social problem, not your problem, with this. My wife used to do record manager. She's very keen on deleting data as soon as you no longer need it. Because if you've got it there, some lawyer wants to read it, and lawyers reading data is very, very expensive. So this is going to tempt people, unless they put the right procedures in place, to just store everything forever and have a nasty shock when some lawyer comes around and wants to read everything together.
Yeah. So in that case, for private data, probably you use your own NAS system and not the cloud.
But you're going to have really good policies and procedures in place, because this can last forever.
Sure, yeah.
That causes, like you said, a legal issue as well.
Yeah.
If the data is around and a court asks for it, you've got to produce it.
I mean, there is, with the same argument, you can argue there has been an accident with a self-driving taxi in San Francisco, Cruise, this General Motors company, where a person was injured, and they could not reconstruct how the accident happened because they didn't store the raw data that were the basis for the decision for AI, for self-driving taxis. They were fined with 1.5 million for not storing data, and the license was withdrawn. So from now on, everyone starts to store every data forever because for liability reasons.
You also drive a truck over one of these things by mistake, and if the court says, you normally say you have to provide it if you can, and if just by accident you drive a truck over some of it, you can probably get out of having to provide it for the courts.
Yeah, so this is also a reason why the amount of data is exponentially growing.
How fast you are accessing this stuff, the processing is going to become a bottleneck soon. But there's so much data out there that even at the fastest possible access speeds, you can't actually process it fast enough to get an answer back.
Yeah, so, I mean, there is much more money put into developing high-performance processing chips than it is put in storage. Don't worry, I think there will be enough money spent onto processing power. Short about the industrialization, I said we are leveraging the existing technologies. Display glass, there is a company in Austria which produced CDs and optical discs. So they are going to produce our data carriers at the beginning. Also, this will be the right module will be integrated with the DMD to make it also, because laser, it's a military class laser, so when you see it, it's the last time you saw anything. So that needs to be encapsulated. There's a Lithuanian company which is leading in femtosecond laser production. And as I said, the robotic library, this BDT just developed a new type of storage which allows a much faster access as they did before.
Are the Chinese expressing interest in this?
Well, they do, but I don't answer. Yeah, so as I said, there is possibility of new use cases. When you combine permanence and fast access and write read and cost efficiency, you can do real-time analytics. So for example, for healthcare, you can access data and create the treatment for a patient on the spot, based on all the experiences. So this is the competition. Someone asked about DNA. So what is around there? The 5D memory crystal, Microsoft Silicon and 𝗧𝗲𝗃𝗃 are identical. So at the beginning, I explained this Memory of Mankind project in the older salt mine in Heidelberg. I wanted to store videos and music also. And I read about these 5D memory crystals, 360 terabyte on this glass disk. And this was a project by the Optoelectric Research Center of Southampton University. It's Peter Kazansky, the more or less inventor of 5D memory crystal. He discovered an effect when you shoot a femtosecond laser, a polarized femtosecond laser, into pure silica glass. It creates parallel lines. Depending on the polarization, the lines have different orientations. Depending on the wavelengths, the lines have different distances. So that's actually some kind of cracks which are appearing. It's a heating up and cooling down, creating these cracks. Interestingly, when I met Peter, I think it was 2014. He could not explain why this happens. With my background as a ceramist, with the silicate technologies, I know that quartz, which is the material of silica, has properties. When you cool down ceramics, you need to be careful at particular temperature ranges because it switches from one volumetric dense volume to another because the crystals are changing over the range of temperature. So I explained him this is a heating cooling effect what you create here, which is in fact the limitation. So you can't write fast, otherwise you just heat up the material and we just start to overheat and melt. So that's a physical limitation of the silica, as I say to all of these three. Another thing is they have incredible data densities. As I said, 360 terabyte in a glass disk like this. At that time when I met Peter, they had a writing speed of some kilobytes, so it took 30,000 years to write 360 terabyte. Now they are a bit faster, so in 2019 they wrote the film Superman, and it took them half week to write it and then a half week to read it. So it's inherent in the material that you can't speed it up. And especially when you write high-density data, write 100 layers of information. We had this discussion before. You need to read through 99 you don't want to read until you can focus on the layer you want to read. So this is why Silica so far only wrote movies on Silica, because the last resort of error correction is to compare frame by frame if there is some black pixel on the blue sky and correct this. And by the way, and Rostron, the chief developer, just left the project, I think months ago. He had a big post on LinkedIn. And as we see also from requests from Microsoft, and interestingly, they call their new AI 𝗧𝗲𝗰𝗵, I think. So abandon the silica for the long-term storage and use it now for their new AI model. Peter Kazansky and his son Ilya Kazansky are taking now over and call it 𝗬𝗲𝗍𝗍onics and offer it as for private people to store their data forever. Here you have exactly your topic. How can I read this data carrier in the future? There is 𝗬𝗲𝗰, holographic storage. It's out there since the 1980s, I think, the first experiments. There's a new company in UK called 𝗬𝗲𝗰, writing into polycarbonate. Same issue, high data density, many layers, poor signal-to-noise ratio. The DNA is also there, I think, since 15 years, the idea to store information on artificial DNA. So they're still very, very expensive and slow. It's chemical processes which take their time. Also reading is slow, and there will be no improvement in the next decades. Actually, a guy from Twist, that was the company investing 150 million into DNA data storage, 𝗬𝗲𝗰𝗵𝗆, he was the chief business developer there. When we met and he came across Cerabyte, he immediately changed to Cerabyte. Is now our director of Cerabyte in the US company. And there is 𝗂𝗀𝗁𝗂. As I learned, you will meet them today also. They are storing on polycarbonate film. And they ask us already when we are ready, because they want to use it for their service in the future. But you will hear about 𝗂𝗂𝗁𝗂 anyway. When you remember this matrix from the beginning, when you have this slow and fast access performance or data access and the cost per terabyte, you can see where these technologies will still be here. Even if you apply Moore's law to DNA storage, it will take 40 years until it reaches the cost per terabyte of today, not in 40 years.
So this graph is for today or for the future?
I think that's valid for the next future anyway.
Martin, you just mentioned existing and improved technology, optical ground disks.
Yes, I didn't mention these. The optical disk, the limitation is the writing and reading speed because, well, one single spot and a limited speed of reading. So, finally about the company, I found, or I met Christian during a presentation at Boston Consulting where I was invited here in Munich on the Alumni Day to the overall theme, legacy and community. And what was funny that Christian already was in contact with me via email because he wanted to celebrate his 50th birthday with his friends in 𝗬𝗏 in the salt mine by putting in a tablet of his life. He didn't read the invitation of BCG because he was going there every year because he was a former BCG employee. And I was very surprised that I was presenting on the stage. So we had a very immediate, very close contact. And he's actually the driver of the technology and the business development. And his nephew, I think, is not his son, his nephew, Alexander is doing the finance. And I mentioned 𝗂𝗏𝗰𝗆 already. So he was working his way through the storage stack from the semiconductor down to the very cold DNA data storage, and then eventually switched to Cerabyte. We could win Steve Campbell, former CTO of Western Digital, to work for us until the Series A round, which will be around mid of the year or in the next coming weeks. And John Colgrove, or 𝗂𝗃𝗃, founder of Pure Storage. So he's also on the board. Steve is CTO. And they give a very valuable input, especially what means coding, what means industrialization. So that was a very valuable collaboration. And still, well, there's still more experts contributing to Cerabyte. Cerabyte officially was founded in 2022 as a startup. We were invited here in Munich to the Intel Ignite accelerator program. I mean, Ignite is a semiconductor producer, but they realized the roadmap has really the potential to fulfill the storage requirements of the future coming from the semiconductor industry. We had this prototype. We have a CERN collaboration. We were invited to Open Lab. So that's just a handful of companies worldwide working together with CERN. So they are testing our data carriers, exposing it to gamma ray, do all the dirty things, and then see how much data can still be read. And they, of course, they have the largest tape library. So they know the next experiments, the next generation of experiments will create 10 times more data. They know what the costs. So they were looking into new storage models. So we have offices in Munich, in Vienna. This is where the party is, on Tech University. We have, I think, in the meantime, 6 labs. We rent space there. Of course, in Silicon Valley, in Colorado, in Boulder, where the storage industry traditionally has their software engineers. We raised seed rounds, got public funding, and are working towards the Series A. So, saving the past, unlocking the future probably is now more understandable than it was at the beginning, why we chose this tagline to describe Cerabyte with a few words. So, that's it. There is the microphone. You can still try to decode with your smartphone reader. Don't touch it, otherwise we need to focus it again. One question.
To wrap up, all the components of your solution are low cost. That's it.
Yeah.
It's you're better than all the other alternatives as DNA or whatever. Mm-hmm. Okay. Why you are alone on this technology? Because we had the luck to patent this completely. So that was a really, really surprise, even for the patent office, when we had our first patent to write data on ceramic on
glass.
Yeah, but
no one had this before.
One has you, okay, it's a technology, and two, it's a market. For the moment, it's just a technology and not a market.
The market is there. If we would have our systems already, we had enough buyers.
But
they're queuing up.
If you're alone, it's not a market.
Oh, okay. So you mean there's a, yeah. So this is why we have several companies as a strategic partner, like Western Digital, like Pure Storage, and there are others from the hyperscalers. They don't want to have it as a kind of monopole, like Silica was for Microsoft. They didn't want to share with anyone else. So everyone wants it that it will be produced in high volumes at the particular costs. Yeah. Yeah, sure. Yeah.
Yes. Your CEO made a presentation 18 months ago in Silicon Valley.
Yeah.
I would like to know what are the main difference between January 2024 and now.
Yeah, so now we can write with 500 nanometers with a new type of laser. More precisely, we used a different kind of stage, which were specially developed for us. So it's improving on every corner. So that's the difference. Yeah.
So, do you have any customers?
We didn't sell anything yet,
okay,
but there is customers queuing up. Yes. Okay. Yeah. I must say it's a big interest from those who store petabytes of data. It's not a consumer product at all. It's not for small entities. It's really targeting this large amount of data where we can really have an impact economically, ecologically.
So what industry verticals are your customers you haven't sold anything to yet, who are developing the product with you and trialing it, etc.?
Yeah, this is our, let's say, banks, national archives, Library of Congress. So when they are ready to store 40 petabyte and so on. So these are the typical first customers, also willing to pay a premium because in the long run, it's still much more cost effective than anything else. It's the medical industry, like genomes. So these are huge amounts of data which need to be processed when they are created, but then kept for. There are no regulations yet for unlimited time. As I also said, the self-driving taxis, there is no regulations how much data and for how long they need to be stored, just in case are stored now.
I mean, Library of Congress and some of that, it's quite interesting because, you know, why would they want this? I mean, Laserfish, that still works. They use things like Laserfish. So why would they want to use this?
Because they want to keep data not only on one medium, so have different media for redundancy, and it lasts. That's the main thing.
But as long as you can see the data, that's the main thing, isn't it? You know, cheaper mediums work where you can see the data if you need it for historical reasons and things like that. This is more expensive.
It's more expensive to retrieve the data from Cerabyte, you think?
No, just it's going to be an expensive system to use.
Well, at the beginning it will be, because the laser is still expensive. That's the most expensive thing. The other components are like commodity, yeah.
Yeah, you were saying in the previous slide that you're innovative, right? Yes, and money this year. Could you be more precise about that?
I don't think I can be precise because that's not public. We will announce it when the round is closed and who are the participants.
Could we imagine to have that before the end of this year?
Yeah, sure. Yeah, sure. Yeah. So it's just a question when we sign it. The more technical progress we have, the more higher evaluated is the company, of course.
So you've got like $14 million so far in seed investment and other contests, funding contests. 14 million. This Series A, do you think it's going to be more than $14 million?
Of course, yeah. It's
going to be above that.
Yeah, the European Investment Bank is offering 15 million as a silent participation for the next round. So that's only a fraction of what we are collecting.
But to my earlier point, this thing I can see it can be stored for a long time, but as other people have asked, it's about accessibility. How do you actually read data? That's why I made the cheap point about 𝗧𝗲𝗃𝗏𝗃𝗏.
Yeah,
it's easy to use.
I mean,
you can see it.
To be precise, I need to emphasize this. The long term is only one aspect. The more important aspect is that we can store data in 10, 15 years at a capacity which the mainstream technologies today will not be able to develop to. So it's rather the main use case will be data stored for decades, not for hundreds of years. It's just a potential. And we already create the possibility to be readable in the future. But the main purpose will be the data created after year after creation need to be on a very cost-effective tier. As the genomes, that's 200 gigabytes per person. If you keep this on flash or on pure, it will be tremendously expensive to store this for 25 years. So that's the time horizon, 25 years of storage. They need to give an offer for 25 years, and no one could actually. It's writing blank checks, actually, because no one knows what the costs in 20 years will be. And here on Cerabyte, the costs appear at the moment when you store data. Then afterwards, you don't have just maintenance costs of the building where you store it. You don't have to climatize it, you don't have to humidity control, and just when you want to read it, you need a bit of energy. So the costs appear and the energy appears during the writing, and then it's more or less zero costs.
Hitachi once offered a 100% guarantee on their systems for 3 years. Otherwise, they'll give you a penalty. Yeah. You're willing to stake a bet that in 20 years you'll be able to read it? Well, and give it money back if they don't?
That's the fine print. That's the fine print. Yeah.
You're looking at security at all. I mean, you could have security on this stuff by physical security. You just lock up the rack in a safe. Yeah. Or you can encrypt the data before you store it, right. In which case it may not be readable because you may lose the encryption key.
That's up to you.
Yeah, well, it is up to you. But it says to me that somebody is going to be selling this technology with services wrapped around it.
Sure, there will be vendors who are...
Yeah, they won't just buy this, they'll buy a complete long-term storage system.
Right, yeah. So there are the typical vendors. I think one is coming today, 𝗬𝗲𝗄𝗏. They're also very interested, of course, into a backup technology where they can calculate the costs over the next 20 years.
Will you be offering a self-encrypting version of this?
If a customer wants to write data, so we have different possibilities to get access to the, let's say, data stack. You have either a A3 access, or hyperscalers want to have their own formats and access on a lower level. So it just depends on the customer where he wants to get his data into the system.
To follow, is it physically breakable?
With a hammer, you can break it, yes.
Like 𝗬𝗏𝗃𝗏𝗏 or...
Yeah, I mean, any data carrier can be struck by a force, yeah. I mean, I have one here, and that's a thicker version that's 300 micron thick because it's easier to handle. And as I said, it's a trade-off of how much you spend on sealing the rim, on what's the actual forces this needs to withstand. So the folding, it's just to demonstrate it. It's never going to be folded.
So if you drop it when you're inserting it, it's going to be fine?
Yeah, like a leaf. I mean, we need to make this test, so if you drop a whole cartridge, what will happen? Yeah, sure. But when you drop an LTO tape, I'm sure it will be hard.
So how much bytes are on one slide now?
Now we have 6 gigabytes per slide.
And you're stating 90 seconds for the first byte?
Yeah.
And you're reading at what speed?
Well, reading, as I said, at the moment it's slow because we don't read with FPGA. Yeah. So it's.
But it's still, so 2030, it's like less than 10 seconds?
Yeah, so...
Speed will go up.
Correctly, yeah. Yeah.
So for digital imaging in hospitals, it will be
good enough.
Probably,
yeah, right. Mm-hmm.
At the beginning of your presentation, you mentioned the 𝗂𝗃𝗃𝗏 memory project in Austria. Mm-hmm. Do you have a partnership with them, and could this become one of the first use cases?
Yes. So I'm still director of Memory of Mankind, but it's a bit on hold now because I need to focus on Cerabyte. But eventually I want to use this technology to store much more data in the Memory of Mankind archive, to create some kind of one world archive. That's an interesting story also. There are small archives of indigenous people who don't want to share their content with the national archive, but they want to share it with a global archive. That will be something like this.